Today we're going to talk about this lovely paper, Noctua, towards automated and practical fine-grained consistency analysis. Right? The title says analysis, but the authors, the paper actually goes beyond analysis, and they say, hey, with this tool, you can run this tool on your software, on your program, and it will tell you what consistency relaxations you can get in your program without sacrificing like the actual functionality, without breaking any invariants and whatnot of your program, right? So it's kind of a tool to optimize the performance of the software. Now they do talk about a specific type of software. So and that specific type is like web servers or web type of web services of some sort, web applications that are backed by a database, right? So they may have a database, and then on top of this database, there is some kind of web application, right? So, and this is how it kind of starts. And this web application, it talks to the database, right? And I think the assumption they make here is this web application, because it talks to the database, and it's kind of one instance of this database. This can be like a, MySQL or something like this. That they kind of get a stronger consistency out of it, right? They don't go into details like what databases they can use. They say it's SQL, and they assume it's some kind of a strongly consistent notion here. They actually, I think, assume it's a serializable type application by default. So, and these are small applications, right? Smallish applications. What happens over time, as the application grows, a natural way to kind of distribute this application is to create more instances of that database, right? More copies, and then have the replication, between these copies. And then next to each copy, you put a new instance of this app. So the app is kind of a stateless, app, right? It gets all of its state from the database. And once you do this, you semantics the serializability. You need to make sure that this replication is synchronous, right? So it's a strongly consistent replication. And again, the paper argues for things like these applications, they grow geographically, right? So this synchronous replication becomes very expensive because of like high latencies and whatnot. So it makes sense to have the apps actually talk to the local copies of the database, right? And get the local state if it's not going to screw up the invariance of the applications, right? So, they argue for the need to synchronize only if the is a chance that maybe in region 1, if they can be like reordered differently, and that will actually create invariant violation, or like will not converge to the same state, right? So so yeah, I guess what they want to do, like in a nutshell, is out of all the possible commands or actions that this application can take, they want to only partially order the commands or the actions that and require that synchronization, right? Only for the commands or actions that can screw up the state or screw up the invariance of the application. So the problem to solve and the type of application that they are working with. And they want, to have this kind of analysis, to figure out what actions the application does, and figuring out whether whether running any two pairs of concurrent actions, any two actions concurrently, will screw up the convergence, right? So if the state, starts to diverge in those different replicas, or if the invariance gets violated, they want to accomplish all of this analysis kind of automatically, right? So they just want to feed the application code into some kind of analysis that will figure essentially whether we need to enforce partial order between any two pairs of actions or not. At the high level, this is kind of their architecture right here, right? So they take the source code of this web application and they feed it into the analyzer, right? So this analyzer has this pathfinder and translator, which is pretty much just a fancy way of saying that they will figure out all the path through the code, right? So they look at the code and they look at all branching in the code and figure out all the path in the code. Now, in their model, the entire state of the application is stored in a database, right? So they actually in the code, they only look, I believe, at the path in the code. And they kind of do it, somewhat statically, but somewhat dynamically, right? So they're targeting Python as their language, and I believe this this whole analyzer, it runs alongside. I freeze. Give me 1 second. Yeah. How much did you miss? Because I tend to ramble and repeat myself a lot.
It's okay, but yeah, I'll let you know if it gets too frequent.
Yeah, sometimes, like recently, my Wi-Fi, if I don't disconnect and reconnect, it does that. I don't know why. So hopefully it will.
Yeah, okay.
So yeah,
maybe turn off your video upload. Maybe that can help.
So we have this. Yeah, I was talking about the high level architecture, right? From source code, they go to analyzer, they find all the path through the code that end up talking to the database, right? Because they only care about the state, the violations of invariance, which are the state of the application, which is the database. This analyzer, it runs alongside the interpreter, right? So it's not like a purely static analyzer. They run in a Python and they check every branching, and then every time there is a database interaction, they capture that and they do something special with it. Right, and that's something special is they capture all these database interactions because they're talking about SQL databases, relational. They capture these database interactions, which are actually again, in their applications are just objects, right? And they're frameworks that translate the objects into the relational operations, and well, not relational, but SQL operations, right? So as they run this analyzer, and every time a code path hits the like database, right? So obviously they record all the branches, like and you know, on whatever the conditions need to take all the branches so that they can like feed this into the you know, the solver later. But they also you know, like as they do, they create this intermediate representation, right? So that they call it SOIR. I'm not sure how to pronounce it, but it's an intermediate representation that goes from like capturing the state, capturing the interactions with the database, and translates it into some kind of language that, or some kind of intermediate representation that is like a bit like more one step removed from the code, or a couple steps removed from the source code. And they use this intermediate representation further to like parse it and actually you know, come up with the like encode it into their solver, you know, come up with like all the I guess conditions and constraints that they need for the solver, and eventually, you know, they use the SMT solver like Z3 to you know, try to find you know, those things that they're looking for. Now, what they are looking for are these two rules, right? So they are looking at a pairwise comparison of different like operations, of different requests, right? So you can kind of imagine that, you know, if I have a, you know, request P and request Q, right? So request P may go through one pass of the code, request Q may go through another pass of the code. What they want to do with the solver is they want to check whether reordering P and Q creates any problems, right? And they do it for all possible, you know, code paths essentially, right? So, and the way they define the problems is with the two rules. So they check for two rules. The rule number one is the commutativity, right? So if P and Q if P and Q commutes, then, you know, eventually, like once you execute P and Q, regardless of the order, you will arrive to the same state. Right? So that's what they express in this rule, you know, where S is the state. If you add, you know, P and then Q to that state, it's the same as adding Q and then P to that state. You know, pretty simple. The second rule that they have, they claim captures all the invariants in your application. So they don't define, they don't make programmers or developers or engineers define the invariants. They claim that the second rule just magically captures all the invariants because their initial application is serial, right? Serializable serial. I think it's actually like totally serial because it's Python, like single-threaded and whatnot. So the second rule is like essentially checking if you know, one action invalidates another action, right? So like the example they give here, for example, like if Q deletes an object that P reads, then clearly Q invalidates the precondition of P, right? So you cannot read P if Q has deleted P, right? If Q has deleted, you know, whatever the P needs to read. So, you know, you obviously cannot reorder those things because there is like a serial nature to those actions. And they claim that serial nature is just encoded, you know, in the code, in the source code, right? Because the source code is like sequential, single-threaded Python code in their case. So they encode these two rules and, you know, kind of use these two rules, and from the intermediate representation, from all the actions, they try all possible permutations, and boom, they find out, you know, the combinations of things that need to be ordered and combinations of actions that need not to be ordered. In my view, there are some interesting things here as well. Like, you know, if this like this commutativity rule is very simple, right? But to me, it looks like it really assumes that all of these actions, you know, whatever the two pairs of actions that they test, like all of the actions that they test, they're kind of atomic, right? So, they can permute the order of P and Q, but I'm not sure, like, it works in such a way that, half of the P has executed and then Q started running, and then, they kind of mix up in that way. So I think that may be like one of the limitations that the system may have, but it's kind of my personal opinion, because the limitations that they list are slightly different. They mention like recursion and loops. They don't support that because these are sources of like unverifiability for the solver. Features that conflict with the way our analysis works. That is not very clear to me, and like some other language features that they just cannot use. So yeah, anyway, I think this is kind of the big picture. They have a few examples in the paper, and they compare what they do with like a few other static analysis approaches for a few other applications. But yeah, as far as like I can tell, the evaluation is pretty much, well, it works. This is how long it takes, and just look like awesome tools, because you don't need to do anything. You just hit the code, and we give you like this awesome analysis.